And welcome back. It's been a little bit since we posted a video, but we've been in the process of getting our 32 cells charged, which you've seen in some of our previous videos. And at this point in time, we do have each of our 32 cells individually charged, and we just have our second bank of 16 assembled, charged, and just a little bit of cardboard. You can see that we've got Kapton taped in place just to protect the terminals. What we have here is what we're getting ready to set up to do. As promised, we're going to do a capacity test on 4 of these 280 amp hour cells. If you remember in the previous video, we were dealing with, we had 4 cells charged up, we put them in parallel. We left them in parallel for a period of time. We let them top balance. And then we hooked them up in series, as you can see here. Now, we have quite a few temporary connections here you'll see with these alligator clips. And what they're going to is the first device, which is receiving its power from the external power supply there. Not that it would skew the results much, but we're using it to be able to see our individual cell voltages. And what this is an ISDT. And right now it is giving us the individual voltage readings for all 4 of our cells. And we were setting about 1 to 2 millivolt deviation. Looks to be about 1 millivolt deviation between our cells at this point. And our second set of alligator clips goes to another set of balance leads, which comes over to our BMS. Now this is a 100 amp BMS that we purchased from BatteryHookup. They didn't have any more of the USB dongles on it, but we have a solution around that. We did take off the included, I think they were 10 gauge wiring, something like that. I had 2 of them, one on the battery minus side, one on the common minus side. This is a common port BMS, meaning both charge and discharge will come out of this side of the BMS where you see the C minus. And this is side here where you see the B minus connects to our batteries. So what we've done is we removed that and replaced it, since we had the very nice pads to kind of solder to. And I've seen other individuals use bolts and connectors, but I went ahead and soldered these. These are 2 1 gauge cables, both for the input of the battery and both for the output, or the common port, I should say, of the BMS. Now this is a 100 amp BMS. May be a little bit overkill for what we're going to do today, but I didn't want to get a smaller ups and push it to its limit. I'd rather have that just a little cushion of margin in there. But again, that's where our second set of balance leads are running to. So our BMS is aware of each cell condition. So in case something should happen to one of the cells during this test or go too far out of tolerance, the BMS will do what it needs to do and go ahead and disconnect the battery pack from everything that you see here. Now what we're using for a little bit of protection, added protection, is just a Class T fuse. That's 125 amp, or I should say, I'm sorry, 110 amp Class T fuse, which is bigger than we're going to be needing for what we're going to be running today. Now, the output of the BMS, again, is a common output. First runs into this disconnect switch here. So in case something should happen, we can manually disconnect this, and that will disconnect our inverter and our load. Then comes over to a Victron Energy SmartShunt, which is outputting data via Bluetooth to this tablet here. Right now you can see that we're about 1.94, 1.95 amps that are being drawn by this BMS just on standby. Well, I shouldn't say standby, it's on the on state with currently no load. And the BMS, I'm sorry, not the BMS that we're using, but the inverter that we are using is a Go Power 3000 watt pure sine wave inverter we'll be using for this test. This is a a little bit older of a Go Power. It used to be the first ups that we ran when we got into solar and we were powering our house. We had just a few circuits like running all the lighting in the house, or maybe the entertainment center is kind of how we started. So we started with a 12 volt standard inverter. This is a 3000 watt inverter. Now the insides of this inverter, this, like I said, this is a little bit older of a Go Power inverter. And you'll see that it says it's actually powered by, I'm not going to try to pronounce that, I'll just get the camera on that. Now, I've seen other individuals take these older ones apart and they have a lot of Samlux parts in it. So these older Go Power inverters, kind of with this square cover, look a lot like Samlux, which also had the similar cover, and also Thor inverters. So I can't speak for the newer Go Power ones, but I can say that we've had this one for many years and it's performed flawlessly, which is one of the reasons why we're going to use it for this test. Because I have run this, like I said, we used to run this in our house, and I've run this particular inverter for days on end, and it didn't even flinch. What we're going to be using for our load is a series of things here. You'll see that highly technical load bar at the bottom with about 5 100 watt light bulbs in it. Gives us the ability to put in one light at a time and slowly ratchet up our load until we get to our target amperage. Now, to be fair, as we stated earlier in a previous video, our batteries are not charged to 3.65 volts. I stopped at 3.5 volts per cell, let them top balance, put them in series, and right before the start of this video, I hooked up our iCharger with a 14 volt power supply, charged them as a series pack with balance leads back up to 3.5 volts per cell. So this test will more than likely fall a little bit short of the 280 amp hour or more goal that we're looking for. With that being said, when the test does terminate and we fall short of that value, depending on how short of that 280 amp hour value we fall, will dictate the results of this test. Now, you may be asking yourself the question, if you're going to be doing a capacity test, why do it if you didn't charge the cells at 3.65? In my case, in my particular solar setup, 3.5 volts is where I'm going to stop charging my cells. I use a BatteryHookup BMS for the house, and I use Victron's what they call long life liable 4 setting, and they have their balancers set to kick in and start bleeding off excess energy at 3.5 volts. I believe it's about 3.5, 3.52 volts per cell, somewhere around in there. And the goal with that is to, yes, you lose capacity, and you lose a little bit of capacity. And if you check out the capacity test videos that the off-grid garage that Andy is doing down in Australia, you'll see that the difference between 3.5 volts and 3.65 volts isn't really that much of a capacity loss. You're still getting a pretty good chunk of the overall capacity of that cell. So again, it's just my preference that I'm going to stop at 3.55 volt or 3.5 volts per cell, but I figured it would still be good to do a capacity test to see what kind of capacity out of these new cells we're going to get when running 3.5 volts, because that will be the mode in which they're run in when they get added to the house system. Without further ado, I'm going to go ahead and cut the camera here, get the inverter started, and get our loads cranked up, and I'll bring you back when we reach our target amperage here, and I'll bring you back in a minute. And welcome back. As you can hear from the cooling fan, we've got our inverter running. We're running about 58 amps. Now our goal for this is about 56 amps. So if you take 280 amp hours times it by 0.2, I believe it's 56 amps. So we're running about 2 amps higher than we wanted for our goal. So I'm going to go come down to our light board here and unscrew that. And that beeping that you're hearing is just our little IDST I forgot to turn the alarm off, so that'll be just a little bit of annoying through this. So we're down to about 52, 53 amps. But our goal for this is to try to be about 56. So it looks like it's going to take all 5 of these bulbs. Yeah, that gives us about 58. So a little about 2 amps higher than we wanted, for slightly higher than a 2C pole. So what we're using is 5 of these bulbs here, as well as a 500 watt shop light that you see running there in the corner. And that gets us pretty close to what we're looking for. So what we're going to do is we're going to continue to run this. We'll come back periodically and check the status of this, and we'll see what goes until either the inverter drops out first or the BMS cuts out. And just in case you're curious, the inverter is rated, maybe you can see that there, for about 10.5 volts. It looks like it's going to be the cutout. And we'll bring you back as the test progresses. Thank you. I want to bring you back for a little bit of an update. According to the Victron energy shunt, we've used about 111.5 amp hours at this point. All of our battery voltages are about 3.2 to 3.22 to 3.24. Looks like the biggest deviation is about 34 millivolts. Hopefully you can see that there. Everything is nice and room temperature, very cool to the touch. All of our bus bars are, again, room temperature. So far, no issues noted. And we're still pulling, as you can see from the screen there, about 58, almost 59 amps. It's about 0.21 to 0.22 C. And we're going to continue to let things progress, and we'll bring you back for another update. Bye. And back for another quick update. About 167.3 amp hours, according to the energy shunt. We're still pushing about 12.59 volts, and I did verify that voltage at the terminals of the inverter with our fluke meter. BMS is still obviously running perfectly fine, no issues. And just a little quick screenshot of our, hopefully that comes into view. We're still pushing about 34 millivolts deviation. Biggest deviation between cells. Everything is still at room temperature, and we'll bring you back for another update as we get closer to the end of the cutoff. Now, as you saw earlier, just a little bit of an update. You notice the inverter has a range of about 10.5 volts, and that equals about 2.6 volts per battery. So the inverter, unfortunately, isn't going to run the batteries down to 2.5 volts per cell. But you know, we'll see how close we get. I'll bring you back a little bit later. Bring you back for another small update. According to the shunt, we've gone through about 242.6 amp hours. We're down to about 12.25 volts. Again, verified on the shunt as well as the inverter itself. You can see our amperage is up slightly. We're up to 60.9 amps. We're up a few amps from where we started. Again, as the voltage of the pack starts to drop, the amperage will start to increase. It's perfectly normal. BMS obviously is still doing just fine. And our per cell voltage readings, we're still about 33 millivolts out. But we're averaging about 3.1 to 3.12 volts per cell. And we're going to let this continue, and we'll bring you back. Thank you. And back for another update. About 265 amp hours. Our voltage has fallen to 11.4 volts. We are now up to 65 amp power draw. Our voltage on our inverter, as you can see from the shunt here, about 11.2. measured at the inverter, 11.42. I'm sorry, I should say 11.41. Sorry for the quick camera work. 11.41, so it's pretty much right on the money as far as what the SmartShunt is reading. And you can see our inverter is starting to flash kind of an amber orange color there, just because the input voltage is starting to drop. And the inverter, again, will shut off about 10.5 volts. Looks like, I think this is, as we saw from the sticker, is its rated minimum. So we got a little bit of headway yet. Again, we're about 266.2 amp hours into this test. BMS is still room temperature, nice and cool, no issues. You can see our battery voltage is here. We're starting to get a little bit more deviation, about 185 millivolts. Cell 1's the lowest right now at 2.7 volts, and 2.9-ish for the remaining. And we're going to continue to let this go until either the BMS shuts off, which the inverter will more than likely shut off before the BMS, but 266 amp hours and continuing, and we'll bring you back. And we're back for another quick update. I'll leave the camera rolling this time until we hit our cutoff voltage, but you can see our voltage is vastly starting to drop at this point. You can hear the inverter starting to beep. It's starting to flash red on the input level as our voltage is getting down to our 10.5 volt mark, which will make the inverter shut itself off at this point. As you can see, we're about 200, coming right up on about 269 amp hours. I'm really hoping we can get about 270 out of here before the inverter shuts down, but I don't think that's going to happen. And the inverter just shut off. So the inverter just shut off at 10.68 volts. And you can see we lost a connection to our SmartShunt at this point because our inverter did shut off. And let's see what we got going here. Yep, 2.5 volts. Looks like our number one cell, actually our number one cell dropped out. So we dropped out at 2.5 volts on our number one cell, which means our BMS stopped outputting power, which is why we lost communication to our SmartShunt, because our SmartShunt is tied into the positive side of the battery directly, but then it needs to get its power through the BMS, so that's why we lost our connectivity there. So it looks like cell 1, again, just kind of coming back to this, cell 1 dropped rather rapidly and stopped. And we were right about 270-ish amp hours out of a 280 amp hour pack. Now, since the BMS shut down, more than likely it shut down when we hit that 2.5 volt mark on that cell, which I would expect. So that tells us the BMS did its job, killed the pack when that first cell dropped below where it should have been dropped for a safety margin. Now, with that being said, is 270 amp hours a bad result? In my case, no, and I'm not going to see the bad result, and here's why. If you remember at the start of this, we started with only charging the batteries to 3.5 volts instead of a full 3.65 volts. So we did leave a little meat on the table. Now, also, again, we're dealing with an inverter here that can only go down to 10.5 volts. So even if the cells would have held out, once it got down to 10.5 volts, which is about 2.6 volts per cell, the inverter still would have shut off. So we were still left a little bit there. Now, a little bit concerning to me that cell 1, which would be this cell here, did kind of drop rather quickly. So what we'll do is we'll get this pack charged up again, and we'll go through another cycle on it and see if our results are the same. Now, typically when you see these load tests done, they'll charge the pack up to a full 3.65 volts, run a complete cycle, and generally if the cells are new, what you want to see is the full 280 amp hours are rated for. And a lot of times, even newer cells, you'll see slightly above that. And then as they cycle a couple of times and break in, they'll come down to that 280 amp hour value. So again, 270 amp hours out of a pack that was only charged up to 3.5 volts, to me is a valid test. Because again, that's where I'm going to use my cells, is in that range of the most they're going to drop, or the most they're going to get charged up to is that 3.5 volt mark. I'm not going to take my pack on a daily basis up to a full 3.65 volts and go from there. So only being 10 amp hours shy of their rated capacity is explainable. Also, you need to take into consideration that, although these alligator clips work for a good temporary measure, they're not as a secure connection as they could be, meaning they're not ring terminals, they're not torqued down to where this BMS would have a more secure connection. And that 2.5 volts that we saw when this dropped out may have not have happened if we've had a better connection on the cells. So take this load test with a grain of salt, that what you're seeing here is completely temporary. And to get this good of a result off of temporary setup, when it goes into the house pack, in which you will have more secure connections, I see 270 amp hour result as completely valid. Yeah, and you'll see that the BMS is still off at this point in time, again, which is fine. And just to let you know, once again, the BMS came from BatteryHookup. It's the 100 amp BMS. Once again, we did remove the wiring that came with it, which it came with 2 of these 10 gauge cables. We just desoldered them and soldered on the 2 1 gauge cables you see here. Again, a bit of an overkill, but they've got very nice wide pads that you could potentially put bolts through and bolt on an actual connector, or in this case, these pads made for a very, very nice wide solder connection point, so we can get a decent gauge cable on there. So we'll be using this BMS for more testing here in the future as well. And I'm very happy with this Victron SmartShunt, with it being able to Bluetooth to the tablet, which obviously it's still disconnected at this point because the BMS has the pack shut off. But one thing I wanted to show you was, so this is kind of stereotypical of a load test, of like a real use load test, where I'm going to have batteries hooked up to the BMS, which hooks up to an inverter and powers various loads. Now, we also got in a new piece of equipment the other day, and this is thanks to Andy at Off Grid Garage, in which he went out and got a very nice 40 amp load tester. And using his links, we went out and purchased the 110 volt version. And you can see here that the plug that came with it is actually not the correct plug for the US. It is rated for 100 volts to 240 volts. But we're going to be using this 110 US. But in a sense, what this is, and when we get it set up, I'll bring you back for another video. This will actually have its own separate video. This runs software that can interface with a computer and will allow us to put very specific charging and discharging parameters on it. We'll be able to take one of these 280 amp hour cells, do a full charge, do a full discharge using a factory calibrated unit that is specifically built for doing charge and discharge tests. It'll also, again, as we said earlier, it'll talk to a computer, so it will allow us to graph that software and export those graphs. So rather than a setup like this, we'll be able to do a lot more controlled, bring a particular cell up to a full 3.65 volt state of charge, let it do a discharge cycle, and you can also program it where once you're done with your discharge cycle and you don't really want to leave your cells in a discharge state, it'll automatically start a charge cycle. And you can vary that voltage. In other words, you can say discharge at a very specific rate or charge at a very specific rate. And once we get this unpackaged and verify that we're good to go, we'll get it hooked up to our bench computer here. Once we clear some room up and get some of this junk cleaned up. And then, like I said, we'll bring you back for video on this. But I do want to thank Andy once again on the Off-Grid Garage for showing this and providing the link of where to acquire this unit. And I'll put his video link down in the description. But that is it of this load test. I'm going to go ahead and start these batteries back on a road of charging, just so they're not sitting here for an extended period of time in the discharge state. And we'll see you in the next video. Thank you.